Hello friends, welcome back to the series on physics of solids. As we saw in the earlier lectures, we have the reciprocal lattice getting important when we deal with interaction between electromagnetic waves and a crystal. Also we discussed that there are three diffraction techniques available to study crystal structure, and we already discussed about the importance of the diffraction, why the diffraction techniques are important, what should be the criterion for the choice of the sources which are used for diffraction. All those things were being covered in the last lecture. So there are three commonly used diffraction techniques available to study the crystal structure, namely XRD or the X-ray diffraction, neutron diffraction and the electron diffraction. Among them, X-ray diffraction is the most safe and economically viable technique. So, for any crystallographer or for an experimentalist in physical sciences, XRD is the technique to start with for analyzing the crystal structure. So, for a student of physical sciences, it is very important whether you are an experimentalist or a theoretician, it is very important to understand how the XRD techniques works and what are the basic what all things which are involved in the analysis of a XRD spectrum. And therefore, in this episode we will basically discuss about XRD or the X-ray diffraction technique. So, what is XRD in brief, right? So, I will tell like this: an electron in an alternating electromagnetic field will oscillate with the same frequency as the field. That is a very fundamental understanding which we developed in the electrodynamics. When an X-ray beam hits an atom, the electrons around the atom will start to oscillate with the same frequency as the incoming beam. Right? Incoming beam is an electromagnetic radiation. In almost all directions, we will have destructive interference. So, because the destructive interference will be the point which will be the major portion will be destructive interference. That is, the combining waves are out of phase and there are no resultant energy leaving the solid sample. So, this is what happens in the normal situation. However, the atoms in a crystal are arranged in a regular pattern, which you all know. That is why the two crystals are different, because their periodic arrangement do differ from between two different crystals. So, the atoms in a crystal are arranged in a regular pattern, and in a very few directions we will have constructive interference. The waves will be in phase and there will be well defined X-ray beams leaving the sample at various directions, provided we are using X-ray beams to probe into a crystal. Hence, a diffracted beam may be described as a beam composed of a large number of scattered rays mutually reinforcing one another in the case of a XRD. And in the case of an X-ray diffraction, we put together all these coherent waves or mutually coherent waves together and we construct a spectrum. So, XRD has the technique of X-ray diffraction has evolved in a huge manner over the years. Like, for the example, in the last lecture I told you about the technique of synchrotron radiations, which are again photons or the electromagnetic radiations which are used for exploring the crystal structure. So, those are very advanced techniques and the technique is still evolving. Now, the technicians in this field are working in a big manner to make this technique available to each and every student in our community. So, there are efforts to make the things cheaper, the technique cheaper, and at the same time there are efforts to advance the horizons of application of the XRD techniques. So, with the help of this of these beams which are producing a constructive interference, we put them together to form a XRD spectrum. So, how does a typical XRD pattern looks like? So, in the figure you are seeing a typical XRD pattern which you will get if you give you a typical sample for to an X-ray crystallographer or an experimental facility where XRD technique is involved. So, what is the y-axis? Y-axis is the relative intensity and x-axis is the Bragg angle. So, we will during this episode we will see these kind of details in bit more detailed manner. So, basically X-ray diffraction works on a very basic optic principle. What is that basic principle? What is it? That basic optic principle is called diffraction. That is why it is X-ray diffraction. So, when does a diffraction occur? A diffraction occurs when light is scattered by a periodic array with long range order producing constructive interferences at specific angles. So, this is the definition of X-ray diffraction which I have formulated specifically for the purpose when we are discussing about the X-ray diffraction. The diffraction may be different and then diffraction can have different definitions according to the context, but this context, in this context this would be a better definition to start with. The next question, why X-ray for structural studies on material science or solid state physics? Why X-ray? As we know that the atoms in a crystal are arranged in a periodic array and thus can diffract light. So, this is the basic characteristic of the crystal. It is not because of the kind of electromagnetic radiation which you use, it is a characteristic of the periodicity of the crystal. So, but here you are aiming at constructive interference, right. So, what should be the criterion? The wavelength of the X-rays must be similar to the distance between the atoms. So, that is why the X-rays. So, what is the kind of wavelength which we are looking at? X-rays are having a wavelength of typically of the order of angstroms, 1 angstrom, 2 angstrom, something like that, which luckily falls to be in the regime of the lattice parameter of the A. So, that is why the X-ray techniques became so much applicable in whenever we talk about the analysis of the crystal structure, because the wavelength of the X-rays and the lattice parameter are quite in good match, they are of the same order of magnitude. Then the scattering of the X-rays from atoms produces a diffraction pattern which contains information about the atomic arrangement within the crystal. So, that is the significance of the technique. And then the fourth attraction about the X-ray is that it is safer and economic than other options available, even compared to the neutron diffraction and the electron diffraction which we listed in our last lecture. Because the next point, point of discussion which you may have already got into your thinking process might be that, does all materials show a sensible XRD pattern? You take any stone or anything or any material in your any solid in your surrounding and you put and you give it to a crystallographer, will it show a sensible XRD pattern? The answer is that there are a major class of materials which will not be which cannot be studied with the help of XRD pattern. So, what are those class of materials? It is amorphous materials. It's like glass, normal glass. So, glass is having a crystal structure, but it is not a regular periodic structure. So, that is why we are called it as an amorphous structure. So, amorphous structures which do not have a periodic array with long range order, they do not produce a diffraction pattern, right. And another set of things with which we cannot study the crystals, with which we cannot utilize the X-ray diffraction might be that it is a technique which is dependent on the electronic configuration of an atom. So, the atomic number of the constituents of the solids are very important when we try to analyze the analyze a solid using XRD. For example, it will be really hard for you to study a carbon only material with the XRD, because carbon is having only 6 electrons. For example, hydrogen or helium, low atomic number below 10, will be really hard to study. Even sodium will be, which is 11, it will be really hard to study with the XRD. And again, another thing is that for mixed materials where you have the crystalline and the amorphous component, the detection limit of this technique would be nearly 2% of the sample. So, one of the essential characteristics of the XRD technique when we choose the appropriate solid for the analysis would be the sample has got to be really crystalline. But again, that does not prevent you from exploring any kind of solid with a XRD technique. It is a very complicated patterning which is also dependent on lot of factors like the what we call as the structure factor, which is not within the preview of this lecture, but structure factor is one single parameter which decides what is the kind of detection limit of an XRD pattern. So, you should always go and explore it. Now, as I told you, all the atoms does not show an XRD pattern. The strength with which the atom scatters light is proportional to number of electrons around the atoms. Now, one of the beautiful thing about the XRD thing is the XRD technique is that even in case where the chemical formula is the same, the XRD may be X-ray diffraction spectrum may be entirely different. As you can see in the figure, I have shown there 3 kinds of silicon dioxide. You have the glass, the quartz, and the another kind of material form of the silicon dioxide, which is cristobalite. So, as I told in the beginning, glass is totally an amorphous material, but it is still silicon dioxide SiO2. But quartz is purely a crystalline form of the same SiO2. As you can see with the blue line over there, blue spectrum over there, that represents the quartz, which is having well defined lines, and I know I can analyze the crystal structure of the quartz with the help of X-ray diffraction. But again, there is a second crystalline form of the silicon dioxide, which is the cristobalite, which is of a slight modification than the quartz. So, X-ray diffraction can essentially distinguish between different crystal structures of the same atomic constituent silicon and dioxide. So, this is applicable for any kind of atomic constituents, need not be silicon and silicon based. So, that is one of the beautiful things about the applicability of these techniques. In the beginning, I have shown you a XRD spectrum, right. So, in the Y you were having the intensity, and in the X you are having the Bragg angle. Now, you are seeing different lines over there. So, if you want to name a lines, what will be the kind of lines names which you would be giving? How will you tag each of the peaks in the XRD spectrum which you saw. So, this tag is dependent on one of the matters which we subjects which we already discussed, which is the Miller indices. So, the concept of Miller indices would be helpful for tagging the peaks in XRD diffraction spectrum. So, each peak in a XRD spectrum is tagged by the Miller indices. So, what is the point of origin of these individual peaks? The answer is very simple. The position of the diffraction peaks in the x axis in a XRD spectrum are determined by the distance between the parallel planes of atoms. How to understand that? This idea can be well understood based on Bragg's law, which you might have studied earlier also. For the study of structure through X-ray diffraction, Bragg's law plays a major role. Bragg's law calculates the angle where constructive interference from X-rays scattered by parallel planes of atoms will produce a diffraction peak. Let me repeat it. Bragg's law calculates the angle where the constructive interference from X-rays scattered by the parallel planes of atoms will produce a diffraction peak. For a crystalline solid, the waves are scattered from lattice planes separated by the interplanar distance. Say we designate it by the letter D, interplanar distance D. When the scattered waves interfere constructively, they remain in phase, since the difference between the path lengths of the two waves is equal to the interior multiple of the wavelength, which is very well which can be very well be understood if you really understood the concept of diffraction from your optics classes. In the figure, I have plotted there a set of lattice planes. So, imagine that you are using X-ray to probe this lattice structure. So, you have the X-rays coming through and then it will be scattered. Imagine that you are taking only those kind of diffracted beams which are producing constructive interference, and the distance between the planes is again assumed to be d, distance between the planes. And if your scattering had happened at an angle theta, then from the figure you will see that the path difference between the waves undergoing the interference is given by 2 d sin theta into 2. Path difference, what is the path difference? Path difference is the difference between the waves, the incoming radiations and the outgoing radiations. So, the path difference can be evaluated as d sin theta into 2, which is 2 d sin theta. So, the derivation of the Bragg's law can be done in various manners. So, if you see the text of Charles Kittel, which is considered as the Bible of solid state physics, there he talks about a very detailed derivation of the Bragg's law based on the reciprocal lattice vectors, which is more prudent and a model to be followed. But for our purpose, for this level of the course, I have with the help of the figure which you saw in the figure there, which you saw in the screen there, you can very easily calculate the path difference between the incoming and the outgoing radiations to be 2 d sin theta, and therefore, the Bragg's law states that n lambda is equal to 2 d sin theta. The effect of constructive or the destructive interference intensifies because of the cumulative effect of reflection in successive crystallographic planes of the crystalline lattice. This leads to Bragg's law, which describes the condition on theta for constructive interference to be at its strongest. In the formula n lambda is equal to 2 d sin theta, n is a positive integer, and lambda is the wavelength of the incident wave. One should always understand what does the n means. N is called the order of the order. So, what is order means by? So, order simply means how many times of reflections had happened before a coherent wave is placed. Like for example, in the figure which we saw already over there, the incoming radiation, the radiation comes and then there is a outgoing radiation. So, it is very easy to imagine that the incoming radiation created an outgoing radiation, right. But in the realistic situation, that does not always happen. This incoming radiation comes up, then there is the outgoing radiation, but actually this outgoing radiation will again reflect back from the one of the planes, and that will again produce another set of diffracted output. So, that is the first order and the second order. So, which is having a first order reflection or the second order reflection, right. But it is one thing is very clear, the phase difference will be constant. So, therefore, we can very easily understood them. But if you take the XRD spectrum, you will see both the first order lines and the second order lines. The second order lines will be the exact repetition of the first order lines. But what will be the difference? Difference would be that second order patterns would be might be of much lesser intensity compared to the first order lines. So, it is the smartness of the crystallographer or a scientist who is exploring the X-ray diffraction pattern to understand which pattern, where does the first order spectrum finishes and where does the second order spectrum starts, and identify the similar Miller indices. But do remember that they are all about parallel planes. Second order spectrum is also from the same kind of planes which produced actually the first order spectrum. So, that will be taken care when you designate each peaks with its corresponding Miller indices. Now, we have already discussed in the previous episode the connection between real lattice and the reciprocal lattice. We also agreed that an electromagnetic wave like X-ray view the crystal in the form of reciprocal lattice, right. It means that a set of parallel planes would be represented by a single plane in the reciprocal lattice. Let me demonstrate that better through this diagram. As you see in the figure, I have put there a set of parallel planes which is corresponding to the real lattice or the real space. Now, based on our class in the reciprocal lattice, we know that we can have a perpendicular to all those parallel planes representing all those parallel planes. So, in the reciprocal space, we will have one single line. Now, if you have a second set of parallel planes like I have shown there in the violet color, there is a new set of parallel planes, and then we draw another the perpendicular line, you will have another second line in the reciprocal space. And now we can have a third set of parallel planes which produce another line in the reciprocal space, and this can go on, and this reciprocal space altogether can be a representative of the real space. And in the X-ray spectrum, you are actually seeing, say imagine that you have only four set of parallel planes like the ones which I have shown in the figure. Then in the reciprocal space, you will have 4 different points of congruence, and therefore, in the XRD you will have 4 peaks. But always one should see that is very clearly easy to understand, because in one of the earlier lectures I showed you the primitive cubic lattices of primitive cubic lattices, and we did derive the kind of planes which are possible in a in a simple cubic lattice. As you can see in the figure, there are 1 0 0 planes, 1 1 0 planes and 1 1 1 planes in the same simple cubic lattice. But it is very clear from the figure that their interplanar distance is different and their orientation are also different. So, therefore, it is that situation which we should be taking into consideration when we are telling that how does a peak originate based on the reciprocal lattice vectors. Now, let us go back to the beginning point where we discussed about a typical X-ray spectrum. Now, you will be able to understand what is the x-axis means by. So, x-axis is the Bragg angle which is 2 theta, n lambda is equal to 2d sin theta. So, that theta is coming over here as the Bragg angle. So, Bragg angle is that angle in which the constructive interference occurred and the intensity with which different planes will be diffracting is totally different based on the electronic density of those planes. Now, so that forms an introduction into the technique of XRD. Now, in the next lecture in this series, we will be seeing what are the applications of the XRD spectrum of X-ray studies and what are the different techniques based on the XRD, of which the powder diffraction will be the most important technique, and how does a powder diffraction, how can one do a real powder diffraction experiment, how can one perform a powder diffraction experiment, and how to derive the data out of a powder diffraction spectrum. And also we will be seeing other techniques like the neutron and the electron diffraction in the coming lectures. Thanks again for keeping your attention with this episode. See you next time.